The Zeeman effect, named after the Dutch physicist Pieter Zeeman, is the effect of splitting a spectral line into several components in the presence of a static magnetic field. It is analogous to the Stark effect, the splitting of a spectral line into several components in the presence of an electric field. Also similar to the Stark effect, transitions between different components have, in general, different intensities, with some being entirely forbidden, as governed by the selection rules. Since the distance between the Zeeman sublevels is a function of the magnetic field, this effect can be used to measure the magnetic field, e.g., that of the Sun and other stars, or in laboratory plasmas. The Zeeman effect is very important in applications such as nuclear magnetic resonance spectroscopy, electron spin resonance spectroscopy, magnetic resonance imaging, and Mossbauer spectroscopy. It may also be utilized to improve accuracy in atomic absorption spectroscopy. A theory about the magnetic sense of birds assumes that a protein in the retina is changed due to the Zeeman effect. When the spectral lines are absorption lines, the effect is called inverse Zeeman effect. Nomenclature. Historically, one distinguishes between a normal and an anomalous Zeeman effect that appears on transitions where the net spin of the electrons is not zero, the number of Zeeman sublevels being even instead of odd if there is an uneven number of electrons involved. It was called anomalous because the electron spin had not yet been discovered, and so there was no good explanation for it at the time that Zeeman observed the effect. At higher magnetic fields, the effect ceases to be linear. At even higher field strength, when the strength of the external field is comparable to the strength of the atom's internal field, electron coupling is disturbed and the spectral lines rearrange. This is called the Paschen-Bach effect. In the modern scientific literature, these terms are rarely used, with a tendency to use just the Zeeman effect. Theoretical presentation. The total Hamiltonian of an atom in a magnetic field is where is the unperturbed Hamiltonian of the atom, and is perturbation due to the magnetic field, where is the magnetic moment of the atom. Therefore, where is the Bohr magneton, is the total electronic angular momentum, and is the Landau factor. A more accurate approach is to take into account that the operator of the magnetic moment of an electron is a sum of the contributions of the orbital angular momentum and the spin angular momentum, with each multiplied by the appropriate gyromagnetic ratio, wherein, in the case of the LS coupling, one can sum over all electrons in the atom, wherein are the total orbital momentum and spin of the atom, and averaging is done over a state with a given value of the total angular momentum. If the interaction term is small, it can be treated as a perturbation. This is the Zeeman effect proper. In the Paschen-Bach effect, described below, exceeds the LS coupling significantly. In ultra-strong magnetic fields, the magnetic field interaction may exceed, in which case the atom can no longer exist in its normal meaning, and one talks about Landau levels instead. There are, of course, intermediate cases which are more complex than these limit cases. Weak field. If the spin-orbit interaction dominates over the effect of the external magnetic field, and are not separately conserved, only the total angular momentum is. The spin and orbital angular momentum vectors can be thought of as precessing about the total angular momentum vector. The averaged spin vector is then the projection of the spin onto the direction of, and for the averaged orbital vector. Thus, using and squaring both sides, we get an. Using and squaring both sides, we get combining everything and taking. We obtain the magnetic potential energy of the atom in the applied external magnetic field, where the quantity in square brackets is the Landau factor Gj of the atom and is the Z component of the total angular momentum. For a single electron above filled shells, and the Landau factor can be simplified into taking to be the perturbation. The Zeeman correction to the energy is example. Lyman-Alpha transition in hydrogen. The Lyman-Alpha transition in hydrogen in the presence of the spin-orbit interaction involves the transitions in the presence of an external magnetic field. The weak field Zeeman effect splits the 1s1/2 and 2p1/2 levels into two states each. The lambda g factors for the three levels are for. Note in particular that the size of the energy splitting is different for the different orbitals, because the Gj values are different. On the left, fine structure splitting is depicted. This splitting occurs even in the absence of a magnetic field, as it is due to spin-orbit coupling. Depicted on the right is the additional Zeeman splitting, which occurs in the presence of magnetic fields. Strong field. The Paschen-Bach effect is the splitting of atomic energy levels in the presence of a strong magnetic field. This occurs when an external magnetic field is sufficiently large to disrupt the coupling between orbital angular momenta. This effect is the strong field limit of the Zeeman effect. When the two effects are equivalent, the effect was named after the German physicists Friedrich Paschen and Ernst D. A. Bach. When the magnetic field perturbation significantly exceeds the spin-orbit interaction, one can safely assume this allows the expectation values of n to be easily evaluated for a state. The energies are simply the above may be read as implying that the LS coupling is completely broken by the external field. However, in a still good quantum numbers, together with the selection rules for an electric dipole transition, i.e., this allows to ignore the spin degree of freedom altogether. As a result, only 3 spectral lines will be visible, corresponding to the selection rule. The splitting is independent of the unperturbed energies and electronic configurations of the levels being considered. In general, one must now add spin-orbit coupling and relativistic corrections as a perturbation to these unperturbed levels. First-order perturbation theory with these fine structure corrections yields the following formula for the hydrogen atom in the Paschen-Bach limit. Intermediate field for J equals 1/2. In the magnetic dipole approximation, the Hamiltonian, which includes both the hyperfine and Zeeman interactions, is to arrive at the Bright-Rabi formula. We will include the hyperfine structure, which is governed by the quantum number, whereas the spin angular momentum operator of the nucleus. Alternatively, the derivation could be done with only the constant is known as the zero-field hyperfine constant and is given in units of Hertz, is the Bohr magneton, under the electron and nuclear angular momentum operators, and can be found via a classical vector coupling model or a more detailed quantum mechanical calculation to be, as discussed, in the case of weak magnetic fields, the Zeeman interaction can be treated as a perturbation to the basis. In the high field regime, the magnetic field becomes so large that the Zeeman effect will dominate, and we must use a more complete basis of or just since n will be constant within a given level. To get the complete picture, including intermediate field strengths, we must consider eigenstates, which are superpositions of the n-basis states. 4. The Hamiltonian can be solved analytically, resulting in the Bright-Rabi formula. Notably, the electric quadrupole interaction is 0 using ladder operators, and we can rewrite the Hamiltonian as now we can determine the matrix elements of the Hamiltonian. Solving for the eigenvalues of this matrix, we arrive at the energy shifts, whereas the splitting between two hyperfine sublevels in the absence of magnetic field is referred to as the field strength parameter. This equation is known as the Bright-Rabi formula and is useful for systems with one valence electron in applications. Astrophysics. George Ellery Hale was the first to notice the Zeeman effect in the solar spectra, indicating the existence of strong magnetic fields in sunspots. Such fields can be quite high, on the order of 0.1 Tesla or higher. Today, the Zeeman effect is used to produce magnetograms showing the variation of magnetic field on the Sun. Laser cooling. The Zeeman effect is utilized in many laser cooling applications such as a magneto-optical trap and the Zeeman slower.